December 18th, 1944. Bastogne, Belgium. The Panther Ausf G rolled to a stop in the frozen mud, its engine still idling. Smoke drifted from hatches where the German crew had abandoned it minutes earlier, fleeing into the Ardennes forest as American infantry from the 101st Airborne closed in. The tank sat intact, its long 75mm gun elevated toward the grey winter sky, its tracks barely scarred, its hull showing only superficial battle damage. Captain James Bates of the 2nd Armoured Division's maintenance company approached cautiously, his breath visible in the December cold. He had heard about these tanks for over a year. Intelligence reports called them the most dangerous armoured vehicles Germany possessed. Frontline tankers spoke of Panthers with a mixture of respect and fear, describing how their guns could penetrate Sherman armour at ranges where American return fire was ineffective. German propaganda broadcasts claimed the Panther represented the pinnacle of armoured vehicle design, superior in every measurable way to anything the Allies fielded. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Now one sat abandoned before him, operational and intact. Within hours, this single captured Panther would begin revealing truths about German tank engineering that would fundamentally challenge everything American tankers believed about their enemy's technical superiority. The mathematics of armoured warfare were about to be rewritten, not through combat effectiveness or tactical doctrine, but through something far more fundamental, the ability to actually reach the battlefield without mechanical failure. The tank bore the number 401 painted in white on its turret. Factory acceptance stamps on the hull indicated manufacture at MAN, Maschinenfabrik Augsburg-Nürnberg, one of Germany's primary Panther production facilities. Serial number 124695, built in September 1944 and belonging to the 2nd SS Panzer Division Das Reich, which had been thrown into the Ardennes offensive as part of the massive German counterattack that would become known as the Battle of the Bulge. American engineers from ordnance units converged on the captured tank within hours. They had explicit orders from the European Theatre of Operations to secure any intact Panthers for immediate technical examination. Intelligence services desperately wanted detailed information about German tank capabilities. Combat units needed to understand the vehicles they faced. And American tank designers wanted to know what made these machines so formidable in battle when they managed to reach combat operations. Captain Bates climbed onto the Panther's hull, noting immediately the quality of the armour plate. The frontal glacis sloped at 60 degrees from vertical, 80mm thick, providing effective protection equivalent to over 140mm against direct fire. The turret mantlet appeared even thicker, a massive casting of armour that no American tank gun could reliably penetrate at combat ranges. The long gun tube stretched nearly 5 meters from the turret face, giving the 75mm KBUK-42 weapon a muzzle velocity that exceeded any Allied tank gun in Europe. From external appearance alone, the Panther lived up to its reputation. This was clearly a vehicle designed without compromise, incorporating every lesson German engineers had learned from encountering Soviet T-34 tanks on the Eastern Front. The sloped armour, the powerful gun, the wide tracks for mobility, the low silhouette for reduced target signature, all reflected sophisticated understanding of modern armoured combat requirements. But when Bates dropped through the commander's cupola into the turret interior, his first impression was of uncomfortable complexity. The fighting compartment was cramped despite Panther's external dimensions. Controls and instruments crowded every surface in arrangements that seemed to prioritize mechanical efficiency over crew comfort. The gun breech dominated the turret interior, leaving minimal space for the 3 crew members who operated in this confined environment. The driver's compartment, accessed through a hull hatch, revealed even more concerning details. The transmission and steering controls appeared extraordinarily complex compared to American tank designs. Multiple levers, each requiring specific sequences and considerable physical force, controlled gear selection and steering. The instrument panel contained more gauges than American tank designers considered necessary, suggesting systems that required constant monitoring rather than reliable automatic operation. Most troubling was the evidence of hasty repairs visible throughout the vehicle. Weld marks showed where components had been reinforced, suggesting design weaknesses discovered after production began. Gaskets appeared to be made from substitute materials, rather than proper sealing compounds. Several access panels had been modified in the field, with new bolt holes drilled to accommodate revised maintenance procedures. This was not the appearance of a mature, refined design, but rather a vehicle still undergoing development, even as it entered combat service. The decision was made immediately to drive the captured Panther to the nearest secure maintenance facility for comprehensive examination. A volunteer crew from the 2nd Armoured Division, experienced tankers who understood the basics of armoured vehicle operation, would attempt the 30-kilometre movement to the division's rear area support base near Neufchâteau. The crew spent 2 hours familiarising themselves with the German controls, working through the starting procedures, and testing each system before attempting movement. Starting the Maybach HL 230 P30 engine required following a precise sequence. The fuel priming pump had to be operated manually until proper pressure built in the system. The electrical system needed to be energized in a specific order to prevent damage to components. The clutch engagement sequence was unlike anything in American tank designs, requiring careful coordination between throttle and clutch pedal to avoid stalling or damaging the transmission. When the engine finally fired, it produced a distinctive high-pitched whine from the Maybach's V12 configuration. The sound was markedly different from the deep rumble of American radial engines or the steady diesel beat of Soviet power plants. The engine seemed to run smoothly at idle, maintaining consistent temperature and oil pressure according to the unfamiliar German gauges. The first attempt to engage the transmission revealed immediate problems. The gear selection mechanism required enormous physical force to move the lever from neutral into first gear. The synchronization, which should have allowed smooth gear changes, seemed barely functional. The driver, Sergeant Robert Chen, a veteran tanker with 3 years of experience operating Shermans, struggled to complete the shift without grinding gears audibly. "This transmission feels like it's already damaged," Chen reported over the intercom. "The synchros aren't catching properly, and the shift effort is way higher than it should be for a vehicle with less than 300 hours of operation." He had examined the hour meter on the instrument panel, noting that this particular Panther had accumulated only 274 operating hours since leaving the factory 3 months earlier. The 30-kilometre drive to Neufchâteau took 6 hours. The Panther required mechanical stops every 5 to 8 kilometres. The transmission overheated twice, forcing extended cooling periods. The steering system required constant attention, with the driver fighting to maintain directional control as the complex steering mechanism responded unpredictably to control inputs. The final drives, which transferred power from the transmission to the drive sprockets, produced concerning grinding noises that grew progressively louder as the journey continued. By the time the Panther rolled into the maintenance facility, Captain Bates knew with certainty that something was fundamentally wrong with German tank engineering. This was supposed to be the finest armoured vehicle Germany could produce. Intelligence reports claimed Panthers were superior to American tanks in every important characteristic. German propaganda broadcasts boasted about Panther invincibility and technical excellence. Yet this nearly new tank, with minimal operating hours and no significant combat damage, had barely completed a short road march under ideal conditions. The transmission, which should have been in near-perfect condition, felt like it was on the verge of catastrophic failure. The final drives sounded like they were destroying themselves with every revolution, and the crew, experienced tankers all, reported that operating the vehicle required constant attention and physical effort that far exceeded anything demanded by American tank designs. The comprehensive technical examination began the following morning, December 19th, 1944. Engineers from Ordnance Corps, assisted by technical specialists from the 2nd Armoured Division's Maintenance Battalion, began systematic disassembly of the Panther's major components. They photographed every part from multiple angles. They measured every dimension with precision instruments. They documented construction techniques, material specifications, and assembly procedures. The examination would continue for 6 weeks, producing a detailed technical intelligence report that would fundamentally alter American understanding of German armored vehicle design philosophy. But the most significant discoveries came within the first 72 hours, as engineers examined the transmission and final drive systems that had performed so poorly during the 30-kilometer test drive. The AK-7-200 transmission, manufactured by Zahnradfabrik Friedrichshafen, lay disassembled across multiple workbenches in the maintenance bay. Engineers stared at components that contradicted everything they expected to find in Germany's premier battle tank. The gear teeth showed wear patterns consistent with several hundred kilometers of operation, not the under 300 kilometers indicated by the hour meter. Several gear faces displayed stress cracks that suggested material quality problems or design loads exceeding component capabilities. Most troubling was the entire design philosophy evident in the transmission's construction. German engineers had created a transmission with 7 forward speeds, which sounded impressive until American engineers recognized that the design was essentially 2 separate transmissions operated in sequence. The complexity was staggering. The weight exceeded 400 kilograms, nearly 3 times the weight of a Sherman transmission. The number of individual parts approached 800 separate components, each requiring precision manufacturing and careful assembly. Lieutenant Colonel Harold Morrison, chief of the technical intelligence team, documented his observations in the official report. The German AK-7-200 transmission represents an attempt to achieve performance through mechanical complexity, rather than through sound engineering principles proven in automotive industry practice, he wrote. The design incorporates numerous features that are theoretically advantageous, but practically unworkable given the realities of combat vehicle operation, battlefield maintenance limitations, and the manufacturing tolerances actually achieved in wartime production. The transmission used straight-cut gears rather than the helical cut or herringbone gears standard in American automotive and tank transmissions. Straight-cut gears were theoretically more efficient, transmitting slightly more power from input to output, but they were also dramatically less durable, requiring perfect alignment and extremely tight manufacturing tolerances to function reliably. Any deviation from ideal operating conditions, any slight misalignment, any tolerance variation in manufacturing would cause accelerated wear and premature failure. American automotive engineers had abandoned straight-cut gears for power transmission applications decades earlier, recognizing through extensive commercial experience that helical gears' superior durability and quieter operation far outweighed the minimal efficiency advantage of straight-cut designs. German tank engineers, lacking this automotive industry experience base, had chosen the theoretically superior solution without fully appreciating the practical consequences. The synchromesh mechanisms, which should have allowed smooth gear changes without double clutching, were barely functional even in this relatively new transmission. American engineers examining the components recognized immediately that the design was inadequate for the loads and operating conditions of a 45-ton combat vehicle. The synchro rings showed severe wear, the detent springs had weakened, the shift forks displayed stress cracks. This transmission might work acceptably in a light passenger vehicle operating under controlled conditions, Morrison noted in his report. But in a combat tank, subjected to hard acceleration, frequent shifting under load, operation by drivers with varying skill levels, and maintenance by field mechanics without precision tools, this design is fundamentally unsuitable and will fail rapidly. The final drive examination revealed even more disturbing truths. The final drives, which transferred power from the transmission through 90-degree right angles to the drive sprockets, represented the single greatest mechanical weakness in the entire Panther design. American engineers disassembled the units carefully, documenting every component. The design used spur gears in a housing that was clearly inadequate for the loads imposed by the 45-ton vehicle. The gear teeth showed stress fractures. The bearings displayed spalling, where small fragments of metal had broken away from bearing surfaces under excessive load. The housing itself showed evidence of flexing, with witness marks indicating that the final drive components were moving relative to each other during operation. a condition that would rapidly accelerate wear and lead to catastrophic failure. Captain Bates measured the gear face width and calculated the contact stress. These final drives are overloaded by approximately 30% based on the vehicle's actual combat weight, he reported. The design might have been marginally adequate for the original 35-ton Panther prototype, but the production vehicle grew to 45 tons, and the final drives were never adequately redesigned to handle the increased load. American engineers had encountered this exact problem in early Sherman development. The original final drives, designed for the 30-ton M4, had shown stress problems when the vehicle weight increased during development. American designers had immediately redesigned the final drives with larger gears, stronger housings, and improved bearings. The redesigned final drives added weight and complexity, but they worked reliably even when vehicle weight increased further in later Sherman variants. German engineers had apparently recognized the Panther final drive problem, evident from the reinforcement welds visible on captured vehicles. But they had never implemented a complete redesign, instead applying field modifications that treated symptoms rather than addressing the fundamental inadequacy of the original design. The materials analysis provided another revelation that troubled American engineers. Steel samples from the transmission and final drive components were sent to metallurgical laboratories for detailed examination. The results showed that German steel quality had deteriorated significantly from early war standards. The alloy compositions were inconsistent, the heat treatment was uneven, the grain structure suggested rushed manufacturing processes that didn't allow proper annealing and stress relief. These components are made from steel that would be rejected as unacceptable for tank transmission use by any American manufacturer, the metallurgical report concluded. The material quality suggests severe shortages of critical alloying elements, particularly nickel and molybdenum, forcing the use of substitute steel grades that lack the mechanical properties required for these demanding applications. This wasn't just an engineering problem. This was evidence that Germany's industrial base was collapsing under the combined strain of strategic material, shortages, and Allied bombing campaigns. The Panther, sitting in the maintenance bay, represented Germany's best effort to produce a superior battle tank, yet the actual vehicle was compromised by material substitutions and manufacturing shortcuts forced by industrial constraints. By December 22, 1944, 3 days into the examination, American engineers had reached preliminary conclusions that fundamentally contradicted the Panther's fearsome reputation. Yes, the gun was excellent. Probably the finest tank gun in the world. Yes, the frontal armor was extremely effective, providing protection American tanks couldn't match. But the vehicle as a complete system was fundamentally flawed by a powertrain that couldn't reliably deliver that gun and armor to the battlefield. Lieutenant Colonel Morrison assembled his findings for the preliminary technical intelligence report. The Panther tank represents a vehicle designed by engineers with limited understanding of automotive engineering principles proven through commercial vehicle development, he wrote. The transmission and final drive systems demonstrate theoretical sophistication but practical inadequacy. The vehicle prioritizes combat performance characteristics, firepower and protection, while accepting mechanical unreliability that would be considered completely unacceptable in American tank development. He continued, German tank designers appear to have assumed that highly trained specialist crews and comprehensive maintenance infrastructure would be available to keep these mechanically complex vehicles operational. This assumption proves incorrect under actual battlefield conditions. The Panther requires maintenance capabilities that exceed those available to German field units, particularly as their logistics system deteriorates under Allied pressure. The most damning observation came in Morrison's concluding paragraph of the preliminary report. Based on examination of this captured vehicle and correlation with field intelligence reports, we assess that Panther operational reliability is dramatically inferior to American tank standards. The transmission and final drive systems, in particular, represent the Achilles heel of German tank design. These components will fail rapidly under normal combat vehicle operating conditions, likely within 150 to 300 kilometers of operation. requiring major overhaul or complete replacement. This assessment would prove remarkably accurate. Intelligence reports filtering back from frontline units throughout the winter of 1944 and 1945 would consistently document Panther mechanical failures at rates that American tankers found difficult to believe. German tanks that looked intimidating and fought effectively when they reached combat were being eliminated more often by their own unreliability than by American firepower. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. January 5th, 1945. Neufchâteau, Belgium. The captured Panther, fully reassembled after its initial examination, sat in the maintenance yard awaiting comprehensive road testing. American engineers had documented every deficiency they discovered during disassembly. Now they needed to understand how quickly these problems would manifest under actual operating conditions. The test program was straightforward. Drive the Panther under controlled conditions while meticulously recording every mechanical issue, measuring fuel consumption, monitoring system temperatures, and documenting required maintenance interventions. The goal was to establish baseline reliability data comparable to the extensive records accumulated from thousands of Sherman tanks operating across all theatres. Captain Bates selected a test route that combined paved roads, dirt tracks, and cross-country terrain similar to actual combat operating conditions. The route measured 150 kilometers, chosen specifically because intelligence reports suggested that Panther final drives typically failed somewhere between 150 and 300 kilometers of operation. If those reports were accurate, this single test drive might demonstrate the catastrophic weakness American engineers suspected. The test crew consisted of experienced tankers who understood proper vehicle operation procedures. Sergeant Chen would drive, following strict protocols to avoid operator errors that might unfairly bias results. The crew would not deliberately abuse the vehicle, but neither would they baby it. They would operate the Panther exactly as they would operate a Sherman during normal tactical movement. The Panther departed Neufchâteau at 0700 hours on a cold January morning. The temperature hovered just above freezing, with patches of ice visible on shaded road sections. These were not ideal conditions, but they represented typical winter weather that all combat vehicles were expected to handle routinely. Within the first 20 kilometers, the transmission problems became impossible to ignore. Third gear, which should have been the primary cruising ratio for road march operations, produced violent vibrations whenever engaged under load. Chen learned quickly to shift directly from second to fourth gear, skipping third entirely to avoid the concerning shudder that rattled through the entire vehicle. Third gear is basically unusable, Chen reported. I can get it engaged, but the vibration is severe enough that I'm worried about damaging other components. Whatever's wrong with that gear set, it's getting worse fast. At 48 kilometers, the first mandatory maintenance stop occurred. The transmission was overheating, with oil temperature gauges indicating conditions approaching damage thresholds. The crew shut down and waited 30 minutes for temperatures to drop to acceptable levels. Captain Bates noted in his log that Sherman transmissions, operating under identical conditions, would not require such cooling stops. The right final drive began making concerning noises at 62 kilometers. A grinding sound, initially faint but growing progressively louder, suggested that gear teeth were not meshing properly. The sound had a rhythmic quality, repeating with each revolution of the drive sprocket, indicating damage to specific teeth rather than general wear. At 85 kilometers, the crew stopped again. The final drive noise had become alarming enough that continuing seemed unwise without inspection. Maintenance personnel removed the final drive cover and found metal fragments in the oil, small chips and slivers of steel, visible evidence that gear teeth were failing under operational loads. The right final drive is destroying itself, reported Master Sergeant William Davis, the senior maintenance technician accompanying the test. These gear teeth are cracking at the roots. We're probably 20 or 30 kilometers away from complete failure, where the gears disintegrate and the whole final drive seizes. Captain Bates faced a decision. Continue driving and document the actual failure point, or stop now and preserve the evidence. He chose to continue. Understanding exactly how these final drives failed would provide valuable intelligence for frontline units facing Panthers in combat. The Panther limped forward. Chen held speed to 15 kilometers per hour, trying to minimize stress on the failing final drive. The grinding noise grew louder. At 117 kilometers, barely 70% of the planned test distance, the right final drive failed catastrophically. The failure was sudden and violent. A tremendous bang echoed from the right side of the hull as gear teeth sheared completely. The drive sprocket locked instantly, causing the tank to slew hard right as the left track continued pulling while the right track stopped. Chen reacted instinctively, immediately, declutching to prevent the transmission from tearing itself apart. The Panther sat immobilized, less than 120 kilometers from its starting point. American engineers examined the destroyed final drive with professional interest mixed with genuine shock. They had expected failure, but the catastrophic nature of the damage exceeded their predictions. The final drive housing had cracked from internal stress. Gear teeth had broken off completely, some sheared at the root, others fractured through the tooth face. Bearing races showed stress fractures. The entire assembly looked like it had been subjected to loads far exceeding its design specifications, yet the operating conditions had been moderate by combat vehicle standards. This final drive was doomed from the moment it left the factory, Master Sergeant Davis concluded. The design is inadequate, the materials are substandard, and the manufacturing quality is poor. Even if you operated this vehicle with extreme care, these final drives would fail rapidly. And in combat, where tanks are driven hard over rough terrain, frequently reversing and pivoting, subject to shock loads from firing the main gun, these components don't stand a chance. The recovery operation required 2 Sherman tanks working in tandem to tow the disabled Panther back to Neufchâteau. The irony was not lost on the American crews. The fearsome German tank, supposedly superior to American designs, needed rescue by the very vehicles it was meant to outclass. During the 40-kilometer recovery tow, neither Sherman experienced any mechanical problems. They simply worked, reliably and without drama, exactly as American automotive engineering principles said they should. The technical intelligence report, finalized in late January 1945, included comprehensive reliability comparisons that starkly illustrated the gulf between German and American tank engineering philosophy. The data came from multiple sources: field, maintenance records from armored divisions operating across Europe, after-action reports from tank commanders, and systematic testing of both captured German vehicles and standard American equipment. Sherman M4, a 3 tanks with 4 GAA engines, averaged 3,000 kilometers between major overhauls under normal operating conditions. Transmission failures were rare, typically occurring only after extreme abuse or damage from enemy fire. Final drives routinely exceeded 5,000 kilometers of operation before requiring replacement. These figures represented real-world performance from thousands of tanks operating in diverse conditions from North Africa to Northern Europe. By comparison, German field maintenance reports captured during the Ardennes offensive documented Panther reliability that was catastrophically poor. The reports, found in abandoned command posts as German forces retreated, provided unvarnished assessments, never intended for Allied eyes. A maintenance report from the 2nd SS Panzer Division Das Reich, dated December 10, 1944, documented that of 48 Panthers assigned to the division, only 17 were operational on the eve of the Ardennes offensive. 13 tanks were down with transmission problems. 9 had failed final drives. 6 had engine problems requiring major repair. 3 were awaiting other mechanical repairs. The operational readiness rate, 35%, meant that fewer than 4 in 10 Panthers could actually fight despite the division being supposedly at full strength for the critical offensive. The report noted bitterly that replacement final drives were unavailable, forcing crews to cannibalize parts from the most severely damaged tanks to keep any vehicles operational. Another captured document, A letter from a Panther company commander to his battalion headquarters expressed frustration in terms that German officers rarely committed to paper. "The final drive problem makes tactical planning impossible," the officer wrote. "I cannot commit my company to any movement exceeding 100 kilometers without accepting that multiple vehicles will become immobilized by mechanical failure. The enemy destroys fewer of my tanks than our own engineering inadequacy." These German assessments matched precisely what American engineers had discovered through examination and testing of the captured Panther. The catastrophic final drive weakness wasn't simply bad luck or isolated manufacturing defects. It was a fundamental design flaw affecting all Panthers, a problem that German engineers understood but apparently could not solve given their deteriorating industrial situation. Technical documents captured at German maintenance facilities revealed that the Wehrmacht was desperately aware of these problems. Engineering change proposals dated as early as June 1943, barely 3 months after Panthers first entered combat at Kursk, identified the final drive design as inadequate and recommended immediate redesign with stronger components. But implementing such changes required retooling production facilities, securing materials that were increasingly scarce, and accepting reduced production numbers during the transition period. The German High Command, facing desperate shortages of armoured vehicles on multiple fronts, chose to continue producing Panthers with known defects rather than temporarily reducing output to implement proper fixes. This decision condemned German tank crews to fighting in vehicles that were mechanically unreliable at best and potentially death traps at worst. A Panther that broke down deep in enemy territory left its crew vulnerable to capture or death. A final drive failure during combat, leaving the tank immobilized under fire, transformed a powerful weapon into a stationary pillbox, awaiting destruction. American tankers facing Panthers in combat quickly learned to recognize this vulnerability. After-action reports from Sherman crews throughout early 1945 consistently noted that disabled Panthers were frequently found abandoned by their crews, immobilized not by battle damage, but by mechanical failure. Lieutenant Thomas Harrington of the 3rd Armoured Division recorded his observations in a letter home dated February 9, 1945. "We came across 3 Panthers yesterday, all abandoned without firing a shot. 2 had thrown their tracks. 1 had a seized final drive. The Krauts just walked away from them. These are supposed to be their best tanks, but they can't keep them running long enough to fight." Staff Sergeant Albert Kowalski, a tank commander in the 4th Armoured Division, noted similar observations. "The Panthers are dangerous when they're working, but half the time they're broken down. We've captured more Panthers due to mechanical problems than we've knocked out in combat. Their crews know the things are unreliable. You can see it affects their tactics. They're careful about when and where they move because they can't count on their vehicles to actually work." The contrast with Sherman reliability was stark and operationally decisive. American armoured divisions could conduct sustained offensive operations, moving hundreds of kilometers, fighting continuous engagements, and immediately preparing for the next mission without extensive maintenance halts. German panzer divisions had to carefully husband their limited operational vehicles, planning movements to minimize mechanical stress and accepting that every kilometer traveled brought mechanical failure closer. By March 1945, as Allied forces drove deeper into Germany, American tankers encountered increasing numbers of abandoned Panthers, many showing minimal combat damage but catastrophic mechanical failure. Final drives were the most common culprit, followed by transmission problems and engine failures. The pattern was unmistakable. German tank designs prioritized combat, performance specifications while accepting mechanical unreliability that made those impressive specifications operationally irrelevant. The strategic implications extended far beyond individual tank capabilities. Germany had invested enormous resources in Panther production, diverting materials, manufacturing capacity, and skilled labor from other critical needs. From January 1943 through March 1945, German industry produced approximately 6,000 Panthers, representing a massive commitment of scarce resources. But these 6,000 tanks never translated into proportional combat power because they couldn't be relied upon to function when needed. A Panzer division equipped with Panthers maintained lower operational readiness than a comparable division equipped with older Panzer IVs, which were mechanically less sophisticated but far more reliable. The Wehrmacht would have been better served producing larger numbers of simpler, more reliable vehicles, rather than smaller numbers of technically impressive but mechanically fragile Panthers. American industry, by contrast, produced 49,000 Shermans during the war, and nearly all of them worked reliably enough to contribute meaningfully to combat operations. The operational availability differential meant that American armored divisions consistently fielded more tanks in actual combat, despite Germany's desperate efforts to achieve technical superiority through advanced designs. The human cost of German engineering philosophy was profound and measurable. Panther crews, knowing their vehicles were mechanically unreliable, faced constant stress beyond normal combat anxiety. They worried not just about enemy fire, but about whether their tank would break down at a critical moment, leaving them vulnerable and potentially condemning them to capture or death. Captured German tankers, interviewed by American intelligence officers, spoke openly about their frustrations with Panther. Reliability. One veteran crew commander from the 116th Panzer Division, captured in March 1945, expressed bitter resentment about the vehicles he had commanded for over a year. "The Panther is a magnificent machine when everything works," he told his interrogators. "The gun is excellent, the armor is strong, the optics are superb. But everything rarely works. The transmission fails, the final drives break, the engine overheats. We spent more time repairing our tanks than fighting in them. And when you need your tank most, when you're in combat or trying to escape encirclement, that's exactly when it breaks down." Another captured Panzer officer, when asked why his unit had abandoned nearly intact Panthers during their retreat, responded with weary resignation. "Why drag broken tanks with us when we know they'll fail again within days? The final drives are destroyed. We have no spare parts. Our recovery vehicles are themselves broken. Better to save the crews than lose. Them trying to recover vehicles that will never be reliable again." The lessons learned from examining captured Panthers influenced American tank development programs for the remainder of the war and into the post-war period. American engineers recognized that German designers had made fundamental errors by prioritizing combat specifications over mechanical reliability and by assuming maintenance capabilities that wouldn't exist under actual battlefield conditions. The final technical intelligence report on the captured Panther, completed in March 1945, included recommendations for American tank development that explicitly referenced German mistakes to be avoided. Future American tank designs must prioritize mechanical reliability and ease of maintenance as equal priorities to firepower and protection, the report concluded. German experience demonstrates that technically sophisticated equipment that cannot be kept operational provides no military value, regardless of its impressive specifications. The report continued. The Germans designed tanks for the perfect battle, where maintenance facilities and spare parts were readily available, where crews were highly trained specialists, and where vehicles operated under controlled conditions. We designed tanks for the actual war, where maintenance occurs in muddy fields, where crews are adequately trained but not specialists, and where vehicles must function reliably under the worst possible conditions. Our approach has proven operationally superior despite the Germans' theoretical technical advantages. By April 1945, as American forces pushed into central Germany, they encountered German tank factories and maintenance depots that revealed the full extent of the Panther reliability crisis. Storage yards held hundreds of Panthers awaiting repair, their hulls intact but their transmissions and final drives destroyed beyond field repair capability. Factory floors showed Panthers in various stages of assembly, with production bottlenecked by shortages of the precision components needed for transmissions and final drives. The industrial evidence confirmed what battlefield experience and captured documents had already proven. Germany had designed and built thousands of tanks that looked fearsome and fought effectively for brief periods, but couldn't be kept operational long enough to provide sustained combat power. The Panther program represented not a triumph of German engineering, but rather a catastrophic misallocation of scarce resources toward producing mechanically unreliable vehicles when simpler, more dependable designs would have served German military needs far better. The captured Panther that had failed so dramatically during American testing was eventually shipped to Aberdeen Proving Ground in Maryland for permanent preservation and continued study. It sat among other captured enemy equipment, a testament to the gulf between reputation and reality, between impressive specifications and actual operational effectiveness. The tank's journey from combat in Belgium to a museum display in America perfectly encapsulated the larger story. Captured after minimal combat use, barely functional after a short test drive, catastrophically failed before completing even moderate operational testing. This was Germany's answer to the Sherman, their supposedly superior alternative, their technological triumph that would shift the balance of armoured warfare in their favour. Instead, the Panther became proof of a fundamental truth about military technology that American automotive engineers had understood instinctively, but German tank designers learned too late. Reliability isn't a luxury feature or a secondary consideration. It is the foundation of operational effectiveness. A weapon that doesn't work when needed is worse than useless. It's a liability that consumes resources while providing no combat value. The Sherman, derided by both German propagandists and later historians as mediocre, proved its worth through the unglamorous virtue of simply working day after day across every conceivable operating condition. American tankers knew their Shermans would start, would drive where needed, would fight when required, and would do it all again tomorrow without drama or extensive maintenance. That reliability, more than any single performance specification, determined who won the armoured warfare campaign in Europe. The Panther, praised for its impressive gun and armour, betrayed its crews through mechanical unreliability that rendered those advantages meaningless. German tankers knew their Panthers might reach the battlefield or might break down en route. They knew the transmission might fail during combat. They knew the final drives might seize during tactical movement. This uncertainty, this fundamental unreliability, negated whatever technical advantages the Panther possessed over its opponents. In December 1944, when Captain Bates first approached that captured Panther sitting in the frozen Belgian mud, he expected to find evidence of German technical superiority. Instead, he discovered proof that superior engineering means nothing without the industrial maturity, material resources, and design philosophy to produce reliable equipment. The Americans had those advantages. The Germans did not. The mathematics were brutal and definitive. The Sherman that actually reached the battlefield beat the Panther that broke down en route. The transmission that worked for 3,000 kilometers outperformed the transmission that failed at 150. The final drive that reliably transmitted power for years of service proved superior to the final drive that self-destructed after minimal use. Germany lost the tank war not because American tanks were individually superior in combat performance, but because American tanks could be counted on to actually reach combat, function during battle, and remain operational for sustained campaigns. Reliability, that unglamorous and often overlooked characteristic, proved to be the decisive factor that no amount of gun power or armour thickness could overcome. The Panther taught that lesson through failure. The Sherman proved it through success. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.